Everyone knows that orange juice with pulp is the superior option when it comes to orange juice. It provides that superior texture and flavor that you just don't get with regular orange juice. So, I have a theory that the majority of high school students in a certain city prefer orange juice with pulp over orange juice with no pulp. But I can't really just say that. I need proof. Proof that the majority of high school students in a city prefer orange juice with pulp. But how do I get evidence of this? The answer is with tests of significance. Tests of significance allow you to make inferences about a population, which is really one of the core concepts of inferential statistics, where you draw conclusions or infer characteristics of a population from sample data. In this video, we'll be specifically covering the hypothesis test for one population proportion. So here I've constructed an example problem that kind of represents our situation. In a survey done by a fruit juice company, 1,100 students out of 2,000 randomly selected high school students in a city stated that they preferred orange juice with pulp over orange juice with no pulp. At a significance level of 0.05, do the data provide convincing statistical evidence that the majority of high school students in this city prefer orange juice with pulp? So when I'm approaching a problem like this, I find it really helpful to read the problem over again and underline key points. So let's just do that here, starting from the beginning. I'm going to underline this 1,100 students out of 2,000. So this tells you a bunch of things. First of all, this is obviously a fraction or a proportion. So this is going to tell you what type of test you want to conduct. So knowing that this is a proportion, I know that we're going to conduct a hypothesis test for one proportion. Secondly, this tells you the sample size or how big the sample was, and that can be represented by n. And we can equate that to 2,000. Lastly, this is the sample proportion, which can be represented by p. And we can write that as 1,100 over 2,000. And this is equal to 0.55. Continuing on, I'm going to underline at a significance level of 0.05. And this is pretty straightforward. What that tells us is that the significance level or the alpha level is equal to 0.05. Lastly, I'm going to underline the last part of the sentence, the majority of high school students. And this is important because this is what we are trying to find out, or what we are trying to prove. Do more than 50% of high school students in this city prefer orange juice with pulp? So now that we have all of this, we can actually start to conduct our test. To start off our hypothesis test, we need hypotheses, which is pretty obvious. The two hypotheses we need are the null hypothesis and the alternative hypothesis. It's important to remember that these hypotheses describe a population characteristic, which is in our case pi, which is equal to the true proportion of high school students that prefer orange juice with pulp. Beginning with the null hypothesis represented by H naught states that the population characteristic is equal to the hypothesized value. or what we think it is. For this problem, h naught is pi equals to 0.5. Moving on to the alternative hypothesis, or HA. The alternative hypothesis states that there is a difference between the population characteristic and the hypothesized value. HA is what we are trying to prove, or what we are trying to find out. In this problem, HA is pi is greater than 0.5. Remember that h naught is initially assumed to be true, so there are only two outcomes. We reject h naught in favor of HA, or we fail to reject h naught. Now that we have our h naught and HA, we can continue the test by checking the assumptions. So I have here a list of all of the assumptions for the hypothesis test for one population proportion. Number 1, P is from a random sample. And this assumption is met because it was earlier stated in the problem already that P, our sample proportion of 1,100 over 2,000, was from a sample of randomly selected high school students. So that assumption is met. Number 2, the sample size is large. This is determined with the following inequalities, which is n, the sample size, multiplied by the hypothesized value, which must be greater than or equal to 10, and n multiplied by 1 minus the hypothesized value, greater than or equal to 10. So I can check that over here. Our sample size, which is 2,000, multiplied by our hypothesized value is 0.5, greater than or equal to 10. So just by eyeballing that, I already know that is true, but just to make sure, 1,000 is definitely greater than or equal to 10. And as for the second one, 2,000, 1 minus 0.5, greater than or equal to 10. Since we know 1 minus 0.5 is just 0.5, the second inequality is true just like the first one. So the second assumption is also met. As for the third assumption, the sample must be no larger than 10% of the population. So our population is all of the high school students in this particular city. And we don't really have a numerical number for this, but we can safely assume that this assumption is also met, as the population is probably very large. So we can assume that this is true. As we learned before, there are only two possible outcomes in a hypothesis test. We either reject the null hypothesis, or we fail to reject the null hypothesis. And this is determined using the test statistic z and calculating a p-value. First, let's calculate the z statistic. This is calculated using the following formula. Z is equal to p minus the hypothesized value all over the square root of the hypothesized value multiplied by 1 minus the hypothesized value over n. We plug in the values and z ends up equaling approximately 4.47. So we can understand this value, we draw a normal curve. Remember that we are working with a standard normal curve with a mean of 0 and a standard deviation of 1. So what this z statistic tells us is that the value of p, our sample proportion, is this many standard deviations away, 4.47 standard deviations away of what we would normally expect if the null hypothesis was true. So that is right here. So then what we want to know is, what is the probability of getting a result greater than that? We can write that as probability of z greater than 4.47. that probability is equal to this area right here. And we can calculate this either using a calculator or a table. I'm just going to use a calculator here. And that comes out to approximately 0.00003914. And this is our p-value. So this is an extremely small number right here. But what does that mean? The p-value essentially shows to what extent your sample data supports the null hypothesis. So for our example right here, when we have an extremely small p-value, that would mean that it would be very unlikely to get this data with a true null hypothesis, meaning that this data is inconsistent with our null hypothesis. If the p-value was higher, such as if it was equal to 0.3914, then it would be likely to get this data with a true null hypothesis. But what if we had a p-value somewhere in the middle? Suppose we had a p-value of 0.04. Then we don't really know for sure whether we should accept or reject the null hypothesis. In this case, we can compare the p-value with our significance level. Compare 0.05 to our p-value. And it's clear that the significance level is much higher. So now that we know all of this, we can move on to the last step, writing our conclusion. Since the p-value is less than the significance level, I can reject H0, the null hypothesis, at a significance level of 0.05. There is convincing evidence that more than 50% of high school students in this city prefer orange juice with pulp. So I guess orange juice with pulp is just better.